discuss the topic. We are in the money time now, and we have a goal for next lecture to prove Moguri superrigidity, and I don't have. It won't be so hard, but we cannot waste too much time. I want to continue. And I didn't say Moguri superrigidity yet. I will do it by the end of this lecture or by the beginning of the next one. But it's some very important theorem, and the proof that I will present is very, very algebraic in some sense. But there is one very important analytic part. And this analytic part, actually, using transcendental methods, is that lemma or that theorem that I will present now. So this theorem is about existence. So somehow this is a general notion theorem. It says that, well, you have something, some universal representation. But we already had one theorem which is non-trivial about triviality of such a representation under quick mixing assumption. The theorem that I present now is about non-triviality of some representation under amenability assumption. So let me do it. Let S be S element. Gamma in S a lattice. T in S amenable non-compact. E.g., maybe T is the group which has just T's here, which is the isomorphic. The ability group R. It's non-compact. It's closed non-compact group. It is amenable because it is abelian. Let G be SLN, SLM, C. And rho an algebraic representation. Consider X, which is S mod T. And this is I want to think about it as a gamma space. Now gamma is the acting group. S is just an equation. Then, and let me use a term that I have so far. We call it, this guy G mod H, we call it the algebraic gate of X. So this is the entrance gate from which X enters the algebraic mode. Whenever X wants to go to the algebraic mode, it must enter that gate. So I'll use that now. Then the gate of S mod T by X is non-trivial. So this is a technical theorem, but it is very important. Actually, introducing some concepts, it would appear a bit less technical than is actually what is going on, and it will be implicit in my proof, but I will say explicitly, is that the gamma action on X is an amenable action.
Excuse me, do you assume any non-triviality role?
Sorry?
Yes.
Yes, for those who weren't here in the first talk, I will remind that an algebraic representation is my assumption with Zoisky density. And maybe actually I want to make another assumption. I want to assume that rho gamma is the Zariski dense and not very compact. Unbounded.
But if the algebraic gain of x is trivial, doesn't it imply that every algebraic action on x
has a fixed point?
is trivial too?
It has a fixed point. The map from x to v is essentially constant. I mean, maybe v has, it's not that every action is trivial, but every action which you can map x must have fixed points, and the map is just the trivial map to a fixed point. And actually, this is what I want to prove now. There is one action which doesn't have fixed points, so one representation with no fixed points. This is what we are arguing now. And again, this appears very, very technical. What's really going on is that the gamma action on S mod T is an amenable action, and this will be part of my proof. And another thing that will go on is that, well, every amenable action either have a non-trivial gate or have a representation into symmetric space. But here we have metric equodicity as well as amenability, and we exclude the other option, and we must have a non-trivial gate. So you may think of this as a combination of more theorems which maybe appear more natural, and this is a bit technical as glued together, but let me prove this. This is something I will use tomorrow in an essential way. So I will start the proof. So first of all, consider the G compact space. So G does act on a compact space, Pn minus 1, Pn minus 1c. It has some natural action on a compact variety.
Sorry.
Yes.
Then, since the triviality of this algebraic gate is equivalent to there being a fixed point of any algebraic representation, then the formulation of the theorem speaking about non-triviality of this gate is a bit misleading, because it says just that we should point a non-trivial action.
This is equivalent under this assumption. We can find, this is what we put, H in G, maybe H prime, it's not that specific H, but this is non-trivial, and a representation X to G mod H.
Yes.
This is what we put. Yeah. So this is very bombastic formulation of that down to earth.
What?
Bombastic.
All right.
Yeah, but satisfied? This is what we're proving. And okay, but what we start by considering G, and it does act on some compact space. This is maybe G mod Q. Well, Q is lambda anything. This G mod, this is some algebraic actually. It's G mod some algebraic subgroup, non trivial of course. Let's see B, the probability, the space of probability measures on this G mod Q. This is a compact coordinate space. So it sits naturally in the dual space C G mod P star, right? So this is a space of measures on G mod P, on G mod Q. And it has a weak star topology. And with respect to this weak star topology, this space here is compact by a one-half theorem, and it has conic structure, etc., etc., etc. So I hope we are all comfortable with these notions. And what I am about to claim first, and this is the amenability I was referring to, is that there exists a gamma variant of gamma act on C via rho. I want to claim there exists a map. Eventually I want to some G mod H, but this will be a starting point. And this is what transcendental method will give us. From X to C. Gamma map. Gamma map means again, and again. Here we have a Borel structure coming from this compact topology. Here this is a Lebesgue space. This is Borel map defined up to Nassau's. It's a map in our category. And again, if you are familiar with amenable actions, this is a standard thing. So I will be brief about formulating it. And what I will just say, S act amenably on S mod T because T is amenable. If S act amenably and gamma is a closed subgroup of S, then also the gamma action is amenable. And amenability of an action is exactly what guarantees such things. I will not use this terminology anymore, but this is just to let you know, if you want to read about amenable action, etc., Zehner's book that I was referring to earlier is an excellent reference, and it will explain the next steps of mine very, very clearly. I will do it in a slightly more ad hoc-ish manner now. Okay? So to prove the claim, find first a map not from S mod T, but from S to C, gamma. This is very easy. Why? Well, because gamma is closed, or actually discrete in S, fix a fundamental domain. Domain F in S for the left gamma action. So this means I'm writing S as such thing. Map F to C arbitrarily. Maybe just fix a point in C and map it all there. Because protect whatever. Just do it measurement, please. And continue it variously for the gamma action. And extend gamma variant using the left gamma action on S and the left gamma action on C. I hope this is very clear. So this task is really, really easy. Again, one may say that gamma acts amenably on S for this. And now I just want to say that there exists maybe another map which is invariant for the T action on S on the right. T does not act on C, but T acts on the space of maps from S to C by its right action on S. And actually, because it commutes with gamma, it preserves the space of gamma equivalent maps. subscript gamma is to say that I'm looking now on the subset of gamma equivariant groups, which is not empty. The non-emptiness is what we observe here.
Why does T commute with gamma?
This is the right action, and this is the left action.
Oh, I see.
It's all about right and left. So, but no politics. It's so okay. Fact that you may know, you may not, and maybe I will explain this in the exercise. Maps SC has a natural compact convex structure. Also, if I will add some close condition of commuting with gamma. Why? Basically, the space of, because this is bounded, this is like some L-infinity space into complicated coefficient space. L-infinity is a dual space, right? L-infinity is dual of L1. So we think of this as an L-infinity functions from S to C, or L-infinity functions from S to this dual space. The pre-dual of this one is L1 function to the pre-dual of that one, to the continuous functions. So this sits naturally in some dual space. And by Banach-Alaoglu, it is compact. Once one of the observers is closed. So now, by the amenability of T, which I was assuming, T has a fixed point for every such action, for every action on such space. A T fixed point, or any T fixed point, is actually a map from S to C, which commute with gamma, but it is T invariant just for the T action on S on the right. So it's a map from S mod T, as required. Is a required solution to that thing.
So this is a complete proof not referring to the notion of amenable action.
Yeah, so I mean, if you happen to know the basic facts about amenable action, you just quote amenability here, and basically what I did here is sketching the proof of amenability of the gamma action on S mod T for you. Okay? This is what I did. But somehow I didn't want to formally define yet another notion and use it. But you can capture all this into one black box, very nicely, very conceptualized one, denoted amenability, and plug it to prove it. Okay? So this is also why I allowed myself to be a bit sketchy here in that part. This is well written in many, many books. Okay. And now, having that, given that, let me hide this, sorry, but only someone is here. I'm using now this claim, forget the proof of it. Having proven the claim, the theorem, let me state now a proposition which will imply the theory. The theory will follow from the following proposition. Now gamma act on X metrically ergodic. observe this is indeed the case in our situation. We are looking at the action of gamma on S mod T. S is SLN, gamma is lattice, T is non-compact. This is the setting we had before. This is the metric ergodic. We cannot map it into metric spaces. In a gamma equivalent way. So now let's take this as an assumption of this proposition. G simple. G less than MC. Gamma goes to G, Z dense, and unbounded representation. And we found some, now it doesn't really matter which, but some Q in G, a real subgroup, and we have some map from X to the probability measure on G mod Q. Gamma map. So this is not yet the algebraic representation we see, right? But it is in some sense close. And this is the setting that we know we have under the assumption of the theorem. We prove this one. And the proposition tells that actually we are done. Then there exists a group which I will call N now for some reason. But strictly contained in H. So this will be and an algebraic representation of X into G mod N. Proving this will prove the theorem. Right? Any questions so far? Okay, so now again it will come a slightly technical lemma. It will be similar to this trick we already used twice by fixing. Okay, here we have some representation of some sort. We will vary Q now and take a minimal guy satisfying this. This will be H of ours. And then we will, but this will be a map to probability measures. And then we'll have to argue that for some other guy, we have actually a map to points, and this N will be the normalizer of that H. Maybe N is not the minimal guy that is guaranteed in that theorem. But it will be something, and there will be some minimal guy, which is even smaller. So this is a strategy. So it starts as things we've done before. It is very similar to a certain proof that we did yesterday. It will be slightly more involved technically, because we have this space of probability measures. So be prepared, but don't be too alarmed. It's not really new. Or maybe just observe. Oh, just let me ask. Are we happy with the statement that the proposition does imply the theorem? So we are reduced to proving that proposition. I will not touch the theorem again until tomorrow when we will use it. So this proof is of proposition, of the proposition. And we start as we know, as we are prepared to start, fix H, minimal. So somehow I'm using the same letter as in the statement of the theorem, but it will not be the same proof. I don't care about the theorem anymore. My notation is now of the proposition. Minimal in the collection maybe let me add adjectives, algebraic here, and see that I forget it here as well. And the collection is all age in G such that we can find maps, gamma maps to prob G mod Q, G mod H. So this is a non-empty collection. G is there, right? We know this. But actually we know better. Also Q is there. We know also that the minimal is less than G. Claim, or maybe let me put this as an exercise for you. Prove that H is non-trivial. Non-trivial. And this is where I will make some remarks and hints about this. This is where we use that gamma is unbounded and that this is metrically ergodic. My claim is that if H was trivial, this means that then we could have mapped X to prob G. And I want to claim that I can find an invariant measure on, an invariant metric, G invariant metric on prob G. One can find an invariant metric on G itself, G invariant metric on G itself. Take the norm metric on the matrices. This is S and C. Just take the usual operator norms of matrices. And whenever you have an invariant metric on a space, you have an invariant metric on the space of probabilities over it. There are various ways to do it. Kontorovich metric, Wasserstein metrics, various constructions that one can do. Usually you want to assume that your metric to begin with is bounded by 1 for integrability reasons. But this is not a problem. We can assume that the metric on G is bounded by 1 and then just take the Wasserstein metric or whatever, no integrability issues, and this will be a metric space. And since the action of X is metrically ergodic over here, we know this by previous work, right? I mean, okay, here we know it by assumption. In the setting of the theorem, we know it by previous work, but we've been there already. So we know that there will be a fixed point here. A G invariant probability measure on G. Sorry, gamma invariant probability measures on G. Can we have gamma invariant probability measure on G? By many ways you can see that not. You can, for example, apply the previous theory that we had yesterday. G is a variety. If we have a gamma is L in that notation. If we have an L invariant probability measure, then modulo the group stabilizing the support of the measure. But now there are no stabilizers for any point in G itself for the G left action. So this age of that previous theorem is trivial, then L or gamma should be precompact. And I'm assuming that it is not. Okay, so this is how to solve this exercise. So I don't need a theorem anymore. So I know two things about my age. Again, what is the proposition? I'm having such a thing, and actually such a minimal thing now, and maybe I just logically fix age, and also I'm fixing the map. Okay, so I now fix the map to a prob G mod H, and this has the minimality property. And I know that H is non-trivial in these two ways. And the proposition claims that I will find some n, but I already told you what will be the n that we will find. It will be the normalizer of H. And now you see the importance of the fact that H is non-trivial. It's not G and not E. So set n to be the normalizer of H. By simplicity, G, n is a proper subgroup of G, and this is this condition that I'm having here. Again, I'm left to show that one. Okay. Consider the Zariski open set in G mod H and G mod H. Maybe I should have packaged it as a black box. It appears in our proof before. Let's set U. To remind you. It is the all XH, YH, such that Y inverse X is not in N. Remember this guy? This is all points in G mod H times G mod H with stabilizer with step contained in a conjugation properly. Contained in a conjugation of H. These are the bad points. So this equation, the fact that it is open, and the fact that these two are equal, etc., appeared in a proof that we had yesterday. And why is it important? Because now I will do this doubling trick that I had before. Consider the map now from X, not to probability measures on G mod H, but to probability measures on G mod H times G mod H. If this is X goes to mu X, this will be X goes to mu X times mu X. This also a nice map into probability measures on a wide variety, right? Now a new claim. So almost every X, mu X times mu X of the bad set is 0. You can believe that, right? If I measure the bad set, I should measure the orbits in it, and this should contradict the minimality of the choice of H. Right, the minimality. But I have to argue a bit more properly because this is not a map to a variety, but a probability measuring variety. So there will be some words to write down. But you see the point. Otherwise, so Svet was not happy with me proving things by contradiction. So it's an exercise to write the proof without using a negation argument. Otherwise, by ergodicity of X, so what I claim is that this number here is some function from X to the ring numbers, right? And it must be constant. For almost every X, mu X times mu X of U is some constant which is not 0. So we can replace our map by a map just that charges only U, we can find a map, a new map. X to probability measure on U by renormalizing. Take the measure μx times μx, restrict it to U, divide by the measure of U, divide by this constant, and get the map into probability measures on U alone. So you have a map, two probability measures on U. Here we have probability measures on U mod G, right? U mod G is not an algebraic variety, but it is a nice case. And this map here is gamma invariant. So the image of X is some point, fixed point here by Ergodic. So the image of X is constant. So this map is constant. And now I apply this integration. This integration says that for every x, I'm getting a map from let me call this y for a minute. From this space y, from this measure space y, I get a map. This is from y from this measure space to probability measures on y. Right, this is this integration. But for me it tells me that you have, whenever I have a map to the space of maps, so actually this is x times y to the probability measures on U. And for almost every y, I can find a map, x, which is the y map, to probability measures on U. Just pick a generic y and you find a map to probability measures on U. And in fact, this map will be the fiber over y. This is the property of this integration. So here I use Fubini. It's not trivial. Right? But what is that? This is prob of G mod H prime, when H prime is strictly contained in some conjugation of H. And this is the contradiction. Contradiction to minimum. Contradicting the minimality of H. H prime appears in this collection, and it is smaller than, or a conjugation of it is smaller than H. Okay, so what did we prove? We proved the claim that we don't charge U. What do we want to prove? We want to prove, let me remind you, that we know that we have this map from X to G mod, to prob G mod H. We know that it double miss the set of points with smaller stabilizers. And we want to conclude that we have an actual map to G mod N. Maybe it is the time to stop and make a nice observation. somehow G mod n, this guy, will appear in some space of measures as delta measures. Whenever we have measures on a certain space, the space itself appears there as delta measure, it's contained there. How do we track delta measures? Here's a nice way. If Z, in solution, if mu is a measure on for mu a measure on Z, so notation should be independent of our story. Mu is a delta measure for some Z in Z, if and only if mu times mu of the diagonal is not 1, when diagonal is, when delta is the diagonal is 1. If you take a delta measure and you take the product of it, it will be the delta measure on the product is 1, yes. If you take two atoms and you take the product space, there will be 2 atoms at the diagonal and 2 atoms outside the diagonal. The more rich your measure is, the less the diagonal is charged. Actually, a measure, maybe another observation, I will not write it down. A measure is continuous if and only if, atomless, if and only if the measure of the diagonal is 0. So this is a nice test to say that something goes to measure. And it appears very naturally in our discussion when we, in any case, discuss doubles. We just try to finish it up. Observe further that considering the natural map G mod H to G mod N, there's an obvious map here, right? And it's double, G mod H times G mod H to G mod N times G mod N. What is the pre-image? It's to you guys. The pre-image of the diagonal in G mod N times G mod N. This is an exercise in basic book theory. So it's a subset of G mod H times G mod H. Now, this is another observation that has nothing to do with our setting, say.
I don't understand. What action there on the right hand side? G mod H times G mod H to G mod N times
Forget actions. Forget actions. No. Yeah, I want you to understand this natural map. G mod H to G mod N. Yeah, we have an action. Canonical map. And then we have this. This is not an action. This is just a double space. So I'm just doubling that map.
Doubling this map.
Yeah, taking, if this is 5, this is 5 plus 5.
Oh.
Okay? It's not indicating any action. And I'm asking, well, here I have the diagonal. This is a closed subset. What will be its pre-image? And this is something we discussed. So this is a subset of this. What will not be in delta? What guys will not be in delta? I claim, and maybe I will leave it for you to check. The guys that will not go to delta is exactly this. So pre-image is the complement. And this is very nice because we know that our measures, mu x times mu x, are supported here. So actually, we know that probe from this observation, we get a probe G mod H times G mod H minus U goes to a probe of the diagonal under this map. I'm probing that map. So I'm probing that map. And I know that my X goes here. And X, where it goes to mu X times mu X. And here it goes to, well, some mu X bar times mu X bar. Maybe mu X bar, let me explain this. If X goes to G mod H goes to G mod N, then X goes to mu X here, and let me introduce this new notation. Mu X bar is the image here. So those measures, mu X bar times mu X bar, are indeed supported on diagonal. And by this observation that we had here, these are delta measures. So we conclude, should I write it down? Conclude. X goes to a probe G mod N is actually contained in, this is the delta map from G mod N itself. And let me remind you that N is not G. And this is what we wanted to achieve. To see if I'm in time. Right. So we proved this proposition, and we proved the theorem that basically every actions of some sort will have a non-trivial algebraic representation. And maybe to end this lecture today and to give a preparation for tomorrow and to explain how this is related, let me not let you go yet.